So now I'm going to do an example where I look at just two objects that have been brought into thermal contact with each other. The first is going to be, I'm going to have 2,000 grams or 2 kilograms of copper. And what I'm going to do, and that's sitting at 80 degrees, that's been in an oven, sitting at 80 degrees C. And what I'm going to do is I'm going to put that copper into a bath of water, which is 500 grams of water. And that bath is sitting slightly below room temperature, sitting at 20 degrees C. Okay. Now for each one of these, it is true that the Q is MC delta T. And of course the masses I've given you. The delta T we'll talk about in a minute. The C is material specific. It turns out for copper, and these are just tables from the book, the value is 0.092. And for water, the value is 1. Again, I said that's why I'm going to use the calories model, because here it's 1 calorie per degree, 1 calorie per degree C gram. Okay, that's the units. Okay, and it's the same units for the 0.092. So now I take this and I say, well, all of these Q's added together have to equal 0. So I've got the Q of the copper. I'll just say Q sub C. Okay, even though the symbol is Cu. Q of the water, together those are going to equal 0. So I've got the mass of the copper, the C of the copper, specific heat, and the delta T. Well, now what's the delta T? Well, I don't know what temperature I'm going to end up at. That's my unknown. But I know that the temperature that I started at is 80. So I'm going to say T minus 80, that's going to be the change in temperature for the copper. Similarly, I've got the mass of the water, the specific heat of the water, and in that case it's T minus 20. Now if you remember, these two things are going to add up to give me 0. That means one of them has to be positive, one has to be negative. And it's taken care of right here because they're going to end up somewhere between 20 and 80. And between 20 and 80, this is going to be a positive number, this is going to be a negative number. So you don't have to worry about the plus and the minus and all those kinds of things. It'll take care of itself. Okay, so what do I have? I've got 2,000 grams of copper. I've got 0.092 as the specific heat of copper, T minus 80, plus mass of water, I've got 500 grams, times 1, and T minus 20. Go ahead and do a little bit of math here, and I've got 184. Right. Yeah, so I got 2 times that, yeah. T, 184T, minus whatever that is, times 80, 14, I wrote that one down, 14,792, plus 500T, minus 10,000. And of course I'm going to gather my T's together. I got 684T. I'm going to take these two both to the other side and get 24,792. Divide and get T equals 36.2. So what I would expect the equilibrium temperature to equal, having done this, would be 36.2. Now a couple things to observe about this. Number one, a lot less water than I had copper, and yet the temperature ends up being closer to the water temperature. It's important to notice if you start at 80 and 20, if you had equal masses, you kind of think, well, with equal masses, it should be halfway in between. It's not, because of C. Okay? And here we've got 4 times as much mass here, yet the water's specific heat is much more powerful. And even though it's 1/4 the mass, it provides more than half of the flow of energy, because what we end up with is closer to the 20 degree than to the 80 degree. So that's an interesting fact. And again, we see that over here. This is 10 times as powerful as the copper, what we see. Now, we could do this experimentally, and we can measure starting temperature, we can measure final temperature, we can measure mass very easily, but something we can't take as a measurable quantity is a specific heat. We can take the assumption that the specific heat of water is 1, and then our unknown ends up being the specific heat of the other material. And that's what I'll do when I actually do lab, is that'll be my unknown. I'll take measurements everywhere else, solve for that, see what value I get, and then compare it to the value that I know should be the value for that material.